Assalamu alaikum. Inshallah, we will be solving paper 5, variant 2, March 2026. Question number 1. Solid X is a mixture of 3 salts, potassium chloride, sodium chloride, and sodium nitrate. The mass of each substance is X in X mixture is investigated by 2 experiments. In each experiment, a different ion is precipitated out of an aqueous solution of X. The mass of each precipitate is measured. A student weighs a sample of bottle containing X and transfers X into a small beaker. The student weighs the sample bottle. The measurements are shown in the table. So the mass of the sample bottle and X is 7.235, and the mass of the sample bottle after transfer is 6.035. Question number 1, complete the table 1.1 to determine the mass of X in a small beaker. It's very simple to get the sample of the mass of sample X. Just subtract the first one minus the second one. Okay, so the mass of sample X equals 7.235 minus 6.035 equal 1.200. So this is the mass of the sample X. Okay, 1.2. Question number 2, calculate the percentage error measurement of the mass in a sample bottle X shown in table 1. This balance, it seems that it measured 3 decimal places. 3 decimal places. So it has an error of plus or minus 0.005, which is 0.001 divided by 2. So this is the error of reading. This one per each reading. Okay. So since we have 2 readings for this one, he is talking about the measurement of the mass of the sample bottle and X. So he is talking about this. He's talking about this part. Only this part, okay? Which is this reading. So to get this reading, we measure, we make the balance at 0 at the beginning, then we measure the mass. So we are taking 2 readings. The first reading is the reading at 0, and the second reading, so the first reading is the reading at 0, and the second reading is the reading at 7.235. So we multiply the error by 2. We multiply here the error by 2. As you can see here, multiply this error by 2, divided by the measured value, times 100 equals 0.0138, equals 0.0138%. This problem is repeated in March paper 5, 2022. The same, he asked to find the percentage error of the measuring of the crucible, and he also multiplied this one by 2. To calculate the percentage error, you have to know something. If you are taking the reading 1 time, so you have to multiply the error by 1 time. If you are taking the reading 2 times, so you have to multiply the error 2 times. For example, using the burette, the error in the burette is 0.1 divided by 2 equals 0.005. Okay, so if you are taking any reading, for example, 10 centimeter cube, and you need to calculate the percent error. In this case, you have to multiply this number by 2 divided by this number by 2 divided by the reading that you will take. So I have to multiply this one by 2. Okay. But in case of, for example, measuring cylinder, we are taking the reading 1 time. So we multiply the error by 1. We multiply the error of, and if the error of the measuring cylinder is 1, so we multiply it only by 1, divided by the reading. Okay. For example, another example, if we said, for example, the graduated syringe is 0.1 is 1 centimeter cube, 1 centimeter cube, the readings. So the error equal 1 over 2 equals 0.5. So the error for each reading is 0.5. Okay. But if we are taking, if we put in the syringe a specific volume and we increase it to another volume, for example, if we put 5 centimeter cube a solution of sodium chloride and we add another 5 centimeter cube of potassium hydroxide, and we need to find the percent error of potassium hydroxide. So we will take the readings 2 times. In this case, we will multiply to get the percent error. We will multiply the 0.5 times 2 divided by the measured value times 100. We have to write here times 100 equal the reading. So the percent error, it depends on how many times do you measure the reading. If you measure it 1 time, multiply the error by 1, like measuring cylinder, or the gas syringe, the measuring cylinder only in this case. Or if you are measuring the reading 2 times, for example, initial and final like burette, so we multiply the error by 2. Okay, we multiply the error by 2. Okay, and all of them at the end we have to multiply it by 100. Okay, and you know that the percentage error equal the error over the measured value times 100. Type question number 2 without changing. Question number 2 without changing any apparatus suggests how the percentage error in one I can be reduced. Type here. The denominator is the error, and the denominator is the measured value. Okay, so if we use larger mass of the solid, so this value will increase and the error will decrease. So to decrease the error of this reading, we have to use larger mass, because if you use larger mass of solid X, so that it will reduce the denominator that result in lower overall percentage error. Okay. But see, describe the steps the student should take to prepare 250 centimeter cube of an aqueous solution. 250 centimeter cube of an aqueous solution of X, starting from the mass of X calculated in 1A. Fine. The mass of X calculated in 1A, which is 1.2. This is the mass calculated in 1A, 1.2. So the mass equal 1.2 grams. This question is repeated many times in paper 5. Number 1, we just get 1.2 and we put it in a measuring cylinder, in a beaker. We put here 1.2 grams. Okay, so then we add distilled water, small amount like 50 centimeter cube, then using a stirring rod and stir it until all of it is completely mixed. Then transfer it to a volumetric flask, 250 centimeter cube volumetric flask, 200 centimeter cube volumetric flask, and this is 200 centimeter cube, so transfer to this one. And when you transfer 200 centimeter cube with the flask, add the contents of the measure of the conical into the flask. Okay, then wash the conical, the beaker, wash it again with water and transfer the washings. Then make up the volumetric flask until the mark, which is 250 centimeter cube. So the steps: number 1, put 1.2 grams of solid X into beaker. Then add a small amount of water and dissolve it so that they are completely mixed. Then transfer them to volumetric flask. Then add water to the beaker again and transfer the whole washings to the 250 volumetric flask. Then make up the volumetric flask until the mark, which is 250, and then every time you add water, just try to steer the volumetric flask, and when you fill it until the mark, just put the cap of the volumetric flask and try to mix it again. Okay, this question is repeated many times, but try to focus on this question. Type aqueous sodium tetraphenyl borate. This compound is used to precipitate potassium. It reacts with aqueous potassium ion to form a precipitate. The ionic equation for this reaction is this one plus this one gives the precipitate, the PPT. Okay, so this compound is irritant. Figure 1.1 shows a Gauss crucible with a porous glass disc. Porous glass disc. This is porous glass disc. The porous glass disc acts as fine filter to separate the precipitate from the aqueous reaction mixture. So the solution formed from solid X is labeled X. The solution, which is formed in the volumetric flask, okay, 250 centimeter cube of volumetric flask, we call it X. In the first experiment, the student carries out the following steps. In the first experiment, the student transfers 250 centimeter cube from solution X. From here, he transferred 200 centimeter cube to 250 centimeter cube conical flask. So he transferred the solution into, he took only 25 centimeter cube of this one, and he transferred them into conical flask, and he labeled the flask D. Use measuring cylinder to add approximately 40 centimeter cube of 0.01 mole per decimeter cube tetraphenyl borate, so that to the conical flask D. So steer slowly until the precipitate forms. So here, after steering, the precipitate here will be formed. So here it will be the precipitate of this compound. Okay, sorry. Leave the conical flask D in ice bath for 20 minutes. Leave it in ice bath for 20 minutes. Then place a clean crucible in an oven for 120 centimeter cube, most properly to remove it, to dry it out. And the mass of this crucible becomes constant, to make it full dry and to get its mass is constant. And to evaporate any water that exists in this crucible. After 20 minutes, remove the crucible from the oven and allow to cool and record its mass. Now we have a clean, dry crucible with a specific mass. Pour the mixture from the conical flask D into the crucible, which contain the precipitate. So now we have the crucible. We have this crucible. Okay, and we have the crucible that contain the filter here. Okay, that contain the filter, and we will transfer this amount here into this one. So the precipitate will remain up. The precipitate will remain up, and the solution will go down. The solution, which is this one, will go down. Okay. So this will be the precipitate. So this one will be the precipitate that contain potassium ion, okay? And this one will be the solution that contain the rest of sodium, which is sodium chloride and sodium nitrate, okay? Pour the mixture from the conical flask in the Gauss crucible. Wash the residue of the Gauss crucible. So we will use the distilled water to wash this precipitate. Transfer the Gauss crucible and the residue to oven and leave it for 1 hour at 120 centimeter cube. 120 centimeter cube. Then remove the crucible from the oven and allow it to cool. Record the mass of the crucible and the residue. Okay. So regarding the Gooch crucible, we will leave it at the beginning in an oven for 100 at 120 degrees Celsius for 20 minutes. Then we will allow it to cool. Then we will transfer the flask D into the Gooch crucible. Okay, then we will transfer the Gooch crucible and the residue to the oven and leave it for 1 hour. Then remove the Gooch crucible from the oven and allow it to cool and record its mass. The first question, other than wearing safety goggles, give one safety precautions that the students must take when handling this precipitate. He said that this precipitate is irritant. So irritant, so it may harm your hands, for example, or your body, so it's better to wear gloves. So wearing gloves is one of the other safety precautions that you have to take in consideration. Number 2, identify the suitable piece of apparatus to transfer 25 centimeter cube of solution X into step 1. And we can use 25 centimeter cube pipette to transfer this amount. Suggest why the volume of NaBC4 sodium tetraphenyl borate doesn't need to be measured accurately in step 2. Of course, here in step 2, we have to just make sure that this amount is excess. This amount is in excess. Why? To make sure here that all the potassium ion are separated from the mixture and precipitate in the form of the compound that is given here. So the exact amount is not important. The most important thing is to make sure that this amount is in excess so that it will precipitate all the potassium ion from the solution. Okay? So it is added in excess to make sure that all K plus ion has been precipitated. So just one reason why the conical flask D is kept cool in ice bath in step 2. طبعا we call it an ice bath for step 2 to decrease the solubility of the precipitate, because if you increase the temperature here, or if you leave here the temperature high, so maybe some of the precipitate will dissolve, right? Because you know that solubility increases when temperature of most solid increases with temperature, and the solubility of the solid decreases with temperature. So when we lower the temperature, we will make sure that no precipitate will dissolve in the solution again. Okay, so especially the precipitate contain potassium ion and it contain potassium ions, so some of the precipitate may dissolve at higher temperature. So this is why we lower the temperature to make the solubility, to lower the solubility of the precipitate, to make sure that we can get the maximum yield that we can get. So just one reason why the Gooch crucible is placed in an oven for 120 degrees Celsius. We said to dry the crucible so that the mass of the crucible will be only its mass without water, or to make sure that we dry it out before using. The mass of the residue is 0 point. So we have here this crucible. We have here this crucible. The mass of this crucible is the mass of the residue here. The mass of the residue here is this mass. Okay, calculate the amount of potassium ion. Calculate the amount in mole. Calculate the amount in mole of potassium ion in solid X in the small beaker. To calculate this amount, we just, number 1, we have the mass of the residue that contain the potassium ion. So to find the number of moles, the ratio between the residue and potassium is 1 to 1. If you look at here the equation, you will find that the ratio between potassium and the residue is 1 to 1. So if you find the number of moles of the residue, it will be the same as the number of mole of potassium ion. So here, the number of moles of potassium of the precipitate equal mass over MR. Mass is this one. This is the mass 0.3579 over the total MR of the compound, which is given here, equal this mass, okay, which is 0.001. Okay. Type. This is the number of moles of this mole, which is 0.001, is the number of mole of potassium in 25 centimeter cube. Don't forget. But we need the total number of mole of potassium ion, which is we need the total number of potassium ion in 250 centimeter cube. So we will multiply, make cross multiplication 0.001 times 250 divided by 25, or 0.001 times 10 equals 0.1. So the amount of K ions in mole equals 0.01. Use your answer in 1D VI to determine the mass of KCl in solid X type. To get the mass equal number of mole multiplied by the MR of the compound type. The MR of KCl equal 39.1 plus 35.5 equal 74.6 grams. To get the mass, the number of mole multiplied by the MR, so this is the number of mole of potassium, or this is the mass of potassium chloride in the compound 0.746. E, aqueous silver nitrate. Aqueous silver nitrate reacts with aqueous chloride ion to form a precipitate of silver chloride. This is famous test for chloride. We just the ionic equation Ag plus Cl minus equal AgCl. In a second experiment, the students repeat steps from 1 to 8, the same steps, but using aqueous silver nitrate instead of sodium tetraphenyl borate. And the mass of AgCl is recorded in step 8 is this mass, 0.215 grams. The amount in moles of NaCl, how can we find it after finding the mass of AgCl? He said you can calculate it using this equation, which is number of mole of potassium chloride, the number of mole of potassium chloride equal Q minus the amount in mole of K in solid X. طيب, the number we need to calculate Q because we have the amount in moles of K, we have it. So we need to calculate Q. Q, which is the amount in moles of AgCl produced when all Cl ions in 250 centimeter cube reacted with AgNO3. So we will make the same as we did for potassium. We will get the number of moles of AgCl in 25 centimeter cube, which is equal the mass, which is 2151, which is 2151 over 143.4, which is the MR of AgCl, as you can see here. The MR of AgCl, as you can see here. Okay, this is the MR of AgCl, grams. And then mass over molar mass equal the number of mole of AgCl in 25 centimeter cube. To calculate the total AgCl in 250, we just multiply this number by 10, equal 0.015. So 0.015 is the total number of the total number of AgCl that present in the solution. Okay. Double I, use the equation 1 to calculate the mass in grams of NaCl present in the solution. So we can use the equation which is given here, N equal Q. We got Q here, which is 0.015 minus the number of moles of K. So Q, which is 0.015 minus the number of moles of K that we got here. We got the number of moles of K here, 0.01. So 0.05 minus 0.01 equals 0.005 mole. This is the number of mole of NaCl. If we need to get the number of mole, the mass of NaCl equals the number of mole multiplied by the MR. The MR is the sodium, the AR of sodium plus the AR of chlorine, which is 35.5 plus 23, equals 0.005 times 58.5 equals 0.2925 grams. So the mass of NaCl equal 0.2925 grams. So now we have the mass of KCl and we have the mass of NaCl in the sample. So, the mass of NaCl in the sample here. So it's easy to get the mass of NaNO3 by subtracting the total mass, which is X, the total mass of X minus the mass of KCl plus the mass of NaCl. The total mass we got in A is 1.2 grams minus the mass of K, which is the mass of K, which is this number, KCl, plus the mass of NaCl, which is this number, equal 0.1615. This is the mass of solid X. Complete table 1.2 to show the effect, if any, on the calculated mass of KCl and NaCl if the residue Kb C6H5/4 wasn't washed in step 6. So here, if the mass here, if this is the crucible, imagine this is the crucible, this is the crucible, imagine that contain the residue. This is the crucible that contain the residue, okay? And in the middle of this crucible, we have the disk, which is porous, okay? And we have the residue. This is the residue. Why do we wash? Why do we wash? We wash to remove the impurities, right? So if we don't wash, so the impurities in this sample, so the impurities of this sample, impurities will stay. That makes the mass of residue greater than the real mass. That will make the mass of the residue that contain K greater than the real mass. So when we calculate the mass of K according to this, we will calculate it plus the impurities. So the mass of K will be higher. The mass of K, the mass of KCl will be higher than the expected. It will be higher than the expected because it includes the impurities. And because of this, when we calculated the mass of NaCl, N equal, we said equal Q minus the number of mole of K plus, right? So if the amount of mole of K plus is more than the actual one, so this value will be lower than the actual value, right? Because Q is constant, 1.2. So if 1.2 minus a higher value, it will give a lower value of the number of mole of NaCl. So the mass of NaCl will be lower than the actual one. So the presence of the impurity will increase the mass of KCl calculated, and it will decrease the mass of NaCl calculated. For example, if we calculate the mass of NaCl, we got it. For example, we got it 0.1. So the number of moles of NaCl equal 1.1 grams. But if it has impurities, so the impurities will increase the mass, right? So imagine that the mass with impurities becomes 0.2. So the number of moles of NaCl will becomes 1. So the amount of mole of NaCl will decrease if there is impurities in the sample. I hope it's clear. Okay. Another student, another student repeated the first experiment but heated the gauge crucible to 320 in step 7. Suggests why the mass of the precipitate collected in this experiment by this student was significantly lower than the mass of the precipitate collected by the first student. But when we increase to 320, the precipitate itself may be exposed to many factors. For example, some of it may be decomposed because we said the mass decrease, right? So some of it may be decomposed, some of it may be melt, some of it may be sublime. Maybe because of some of this precipitate may decompose by heat, so the mass of the precipitate will be lower than the actual mass. And this is question number 1. That's it. Question number 2, plasma. Blood plasma contains a number of different cations. Many of these cations emit a different color of light when placed in a flame. The flame emission photometry is a method of determining the concentration of cation in a sample using the intensity of light emitted. So we can use the concentration using the intensity of light. In an experiment, a sample of blood plasma is placed into a colorless flame. K plus ion in the blood plasma absorb energy from the flame and emits light, which is lilac color. And we know that the flame test of potassium is lilac. The intensity of the light emitted is measured. To determine the concentration of K ions in the sample, a calibration graph showing the relationship between the known concentration and the intensity of light is required. Right. And we will make, through this experiment, we will make the calibration graph, which is a relation between the concentration and the intensity of light produced by potassium ion. A solution of potassium chloride is prepared. The concentration of the potassium ion is 0.1 gram per decimeter cube. A different volume of solution KCl are taken and diluted by specific volumes of distilled water to prepare solution of a specific concentration. And as if we'll diluted. Okay, but each prepared solution of K plus is tested using the flame emission photometry, and table 2.1 shows the relative light intensity measured from each prepared solution. Question I, complete the table 2.1 to show the volume of the distilled water added to make each prepared solution. طبعا we will add KCl to distilled water. Okay, so the sum of them always should be constant. The sum of them to make first test, the sum of them should be always constant. So at the beginning, without addition of any KCl, we will add 50 centimeter cube. Don't forget that it should be 2 decimal points because we are measuring from the since we have 2 decimal points, so we can measure it by using the rate. But if we put half centimeter cube of KCl, so the volume of water should be 49.5, so that the sum equal 50. If we put 1 gram per decimeter, centimeter cube, so the volume of distilled water should be 49. If we put 1.5 centimeter cube, the volume of distilled water should be 4.8, and so on until we reach 5 centimeter cube of KCl and 45.00 centimeter cube of distilled water. In each time we get the relative light intensity and the concentration. Here the concentration is 1.00 times 10 power minus 3, and the light intensity is 2.1. Then here the mass, which is the concentration, which is the mass in gram divided by the concentration in centimeter cube, divided by, the volume in centimeter cube, equal 2 times 10 power minus 3. So the light intensity in this case is 4.2, and so on until we reach to this the final readings. Okay, it seems from the reading, and after this concentration, after 8, the light intensity is constant. When we change the concentration, the light intensity is constant. This means that the flame or this method, until after this concentration, we can't use it anymore to measure the light intensity of the solution that contains K. Okay, from the readings, it can't measure any other light intensity after this concentration. Okay, طيب. Identify the suitable piece of apparatus. طبعا we said to measure or to add distilled water. Since we have here 2 decimal points, all of them should be 2 decimal points. All of them, to take the mark, all of them should be 2 decimal points. So the suitable tool to measure this 0.00 accurate readings, we should use burette. Type. What is identifying the dependent variable? طبعا the independent variable is the concentration that we are changing, the concentration of K that we change by using distilled water and KCl. This is dependent, and we measure according to it. We measure the light intensity. So the light intensity is the relative light intensity is the dependent variable. The dependent variable. Okay. So the independent variable is the concentration because we change it. So the independent, I think you know this, independent is something that we change. But the dependent is something that we measure. Okay? Right. Plot a calibration graph on the grid in figure 2.1 to show the relationship between K plus and the relative light intensity. Use the cross to plot each data point. Drew one line of the best fit for K plus from 0 times 10 power minus 3 until 7. Then draw the second line of the best fit from starting from 8 times 10 to the power of minus 3 until the last reading, and extend both lines so that they meet. When we plot, طبعا هنا each small square, if you notice here, the difference is 2. So to get the reading of the small square, we just say 4 minus 2 divided by 10 equal 2 divided by 10 equals 0.2. So every 2 small square is 0.2. So this one, for example, is 0.2. This one is 0.4. This one is 0.6. This one is 0.8. This one is 1, and so on. Okay. And here also 2 divided by 10. So also this one equal 0.2, 0.4, 0.6. Here 1. Okay. 2. Here 3, and so on. Here 4. Here 5. And so on. And this is the relation between the concentration of potassium ion and the relative light intensity. But when we plot the points, and try to get the graph, make sure, and this is very important, make sure that the line should be of the best fit. What does the best fit mean? Yani it comes out from the origin, because he said here at 0, the light intensity is 0. So it comes out from the origin. Okay. But then if you notice that this point on the graph, and this point above the graph, and this point below the graph. So the number of points above the graph and the number of points below the graph are almost equal. And the number of points on the graph, okay, no problem. Okay, so this is how to draw the line of the best fit. And since all of them are shown on the same line, so the line of the best fit is a straight line because all of them on the same line. And it is very clear that this point is anomalous. This point is anomalous because it doesn't fit the rest of the results. So this is the first line, and this is the second one. When we extend both of them, they will intersect here. Okay. Describe. Question 1, describe, or V, describe how the graph shows that K, the concentration of K from 0 to 7 times 10 power minus 3 is directly proportional. طبعا it's clear from the graph and the relation is a straight line passing to the origin. So the relation from the graph is direct proportional. Circle the most anomalous point. Circle the most anomalous point. As we said, this is anomalous point on your graph, and suggest one reason why. One reason to explain the anomalous point. Type here at 6, the concentration 6. Okay, if we consider that we measured the concentration right, so the intensity should be, the intensity of light should be here, for example, which is like 13.2, but we got it at 6. We got it 11.2. So this means that the light intensity is lower than the expected value. Lower than the expected value. This may happen if we consider that 6 times 10 power minus 3 concentration is correct. We prepare it correct. So the flame may not clean so that it doesn't produce the suitable intensity, the suitable light intensity. So maybe if we consider, or if we make sure that the concentration is prepared well, so maybe insufficient cleaning of the flame. This is why it doesn't produce this intensity. Or maybe the flame is good, but the concentration prepared is we put too much water, and we diluted too much, and we didn't measure the exact amount of water to dilute the solution. Okay, or we didn't record the correct amount of, and here maybe we put more than 47 distilled water. Too much water is added, so the concentration become very diluted, or this amount is not measured in the correct way. Okay, so these are the reason why we get intensity lower than the expected value. A sample of blood plasma is diluted 100 times and tested using the flame emission photometry. The light intensity recorded 3.8. Use your graph in figure 2.1 to determine K plus in gram per decimeter cube in the sample. But 3.8, if the light intensity is 3.8, so here is 3.8. This one is 3.8. So we just make a line, extend it to the graph, to the line graph, then move it down. You have to show your work on the graph. So this will be the concentration, which is 1.6 times 10 to the power of minus 3. 1.6, this one is 1.6 times 10 to the power of negative 3. So the K in the diluted plasma equal 1.6 times 10 to the power of minus 3. The healthy range of K plus, the healthy range of potassium ion in our blood, or in the blood plasma, between 0.1 and 0.2. State whether the sample of the blood plasma tested in 2BI is within the healthy range, too high or too low. Explain your answer. So we got it here, 1.6 times 10 to the power of minus 3. But the sample diluted 100 times. So the actual concentration of the blood, in this case, equal the actual concentration of K in the blood equal 1.6 times 10 to the power of minus 3, the concentration, times 100, because he said he diluted the blood 100 times, equal 0.16 gram per decimeter cube. 0.16 gram. And since 0.16 gram exists in this range, which is the healthy range, so this concentration that indicates this light intensity exists in the healthy range. Question number 3, when testing samples of blood plasma, a colored light filter needs to be used, which only allow lilac color light emitted from the sample to reach the detector. So just why this colored filter is needed when testing the blood plasma, but not necessary when testing the KCl, because you know that in the blood plasma, in the blood plasma, we have more than one ion. We have sodium ion, we have potassium ion, we have calcium ion, and we have many ions in the blood. We have many ions. We have magnesium ion. We have many ions in the plasma. So when we make the relative light intensity, it may produce more than one color. So the flame test, it may produce more than one color. It may produce more than one color. These colors, okay, to avoid them, we have to filter, because I need only the lilac color. So the yellow color produced by sodium, for example, I don't need it. So we have to put filter. We have to put filter. This filter only can choose the lilac color and stop the rest of the color from passing. But in case of KCl, we have only K ion, so we don't need filter, because we only have K ion that produce lilac color. So we don't have filter. We don't need filter at all. Explain why the flame emission in photometry is not suitable for measuring the K ion at 8 times 10 power minus 3. As you can see here, after 8, it becomes constant. After 8, the graph becomes constant. So why do you think that? Because we said that after 8, according to this graph, after 8, the graph is level off. The graph is level off. Okay? This means that at this concentration, when we reach to 8 times 10 power minus 3, any other concentration is no longer result in a change in light intensity. If you add any more concentration after 8 times 10 power negative 3, after this concentration, 9, 10, 11, 12, any other concentration doesn't result in a change in the light intensity. Okay? Okay? D, state whether the data used in calibration graph are reliable or not. This question, if you look at most of the results, you will find that most of the results exist on the same line. Most of the results exist almost on the same line. Most of them, except only this one, except only one reading. So reliable, yes, they are reliable, as most of them lie on the same. As most of them lie on the same line. Most of them touch or lie on the same line, except only one reading. So only one out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One reading out of 11 out of the curve doesn't make the readings non-reliable or unreliable. So yes, they are reliable because most of the points are very close or lie on the line of the best fit, showing a clear trend. The trend is very clear. But if we need to avoid, if he asks you to avoid the anomalous point, just repeat this reading again. Okay? That's it. Thank you.